Concentrated, diluted, right? All right. What's V of T?
Volume.
No, I'm specifically for what we did today.
10 now?
10. Yeah. 10 volumetric flat. What's the V of C?
1.
Yep. And where do we get that? Yeah. Okay. Rock on. Okay, so that's part 2. Now, in part 3, we're going to take your solution A and we're going to do an extraction.
Oh, that's a good idea. We're probably going to be here a while, though. Maybe it'll be less.
It's honestly just like another open lecture. Except this one I'm not.
Okay, come back. Sorry. Okay.
Question.
Yeah.
Should we turn these on?
Yeah, sure. Not a bad idea. Okay, so we're going to do an extraction, okay? It's where you take something out of something. Probably many of us did an extraction this morning. I do it every morning. It's the first thing I do. If I don't do it, ain't nothing going to happen. What's that extraction I did?
Flossing.
What's that?
Flossing.
I wish I did it every morning.
Hurry.
Once a day. Once
Oh.
a day. I mean, I get in there. No, coffee. Yeah, I extracted caffeine, precious caffeine out of coffee grind. Right? That's a liquid solid extraction. What we're going to do today is a liquid extraction. Okay. So, abandon my Roman numerals. Part 3. A liquid extraction. Okay. What a liquid. This is not turning
Is
on.
there a button on this?
It's in the back. Yeah.
It is.
She doesn't have a button on the back.
Oh. Okay.
Try turning it on.
Sorry.
Oh well, let's, it's not, it won't be totally warm, but it's not really going to affect us too bad. Okay, so in a liquid extraction, what you're going to do is you're going to mix 2 immiscible solvents together, okay? Miscible means they don't mix. They make 2 different layers. The visual I always suggest is Italian dressing when it's just sitting on the shelf in your refrigerator. Yeah, it's got 2 different layers. Okay. So we're going to do this physically in a culture tube. This is a culture tube. It's the one that's got threads on the top. Okay. And so you're going to take culture tube. Right. And you're going to have 3 mils of your solution A, and you're going to have 3 mils of 2-octanol. Okay? The octanol is the organic layer. Alright, and it will always be on top. Most of the time, organic layer is on top. Not always, though. And actually, we're going to do one fairly soon where the organic layer actually is on the bottom. But in general, the majority of organic solvents are less dense than water, so the water is on the bottom. Alright? And let me take a moment to note that you can't put octanol in these instruments and get a reliable reading. You can only put aqueous solutions in these instruments. So we're going to assess these extractions we're doing by examining the aqueous layer. Okay? All right, and so just like with Italian salad dressing, if you put you've got 2 solutions that are immiscible in here, we're then going to put Teflon tape around these threads. Okay, Teflon tape makes plumbers use it a lot for threads if you don't want it leaking. Okay, and then you just wrap it around, it tears right off, and you put on your, if you're really being careful, put the Teflon tape on so that when you tighten the cap, it's going the same direction. It lays the tape down rather than undoes the tape. That makes sense. Okay. And then when you do an extraction, an important rule is that first shake is gentle. Okay. There are things that can generate gas. All right. One time I did an extraction with a big piece of glassware about this big, and I forgot that it rolled. And because I didn't realize there was an impurity in here that caused a lot of gas. And I had this piece of glassware, and I had it at the top, and I had it at the bottom. And I went, like that. And it exploded. And I had the top little piece of glass, and I had the bottom little piece of glass, and I was drenched in chemicals. So anyway, that first shake you do, whenever you do an extraction, not my finest moment, you do a gentle little shake, and then you just like if you were opening up a brand new soda, okay? So that any gas pressure can be released. All right, okay, no, that's okay, I can be a little bit more aggressive. Okay, get it shaken up for you, okay? When you do that, some of that methyl violet is actually going to go into the 2-octanol. Okay? And so we'll shake it up, we will then put it in the centrifuges. Okay. What's the most important rule about using a centrifuge? Balance. Yeah, exactly. So the easiest thing is wait for somebody else that's ready to do it, and then put it in the centrifuge, socially distanced, like this. Okay. You can put in 2 that are opposite each other. Okay. I think those ones will take up to 6. And you can put in 6. So if 6 of you are ready to go right at the same time, then you just got to make sure that it's balanced, that there's 3 opposite each other. All right. You'll centrifuge it. That helps. You could wait, just like salad dressing. Eventually, it'll again. You could wait, but to hurry up that separation, the centrifuge will make the more dense stuff go down the water, and less dense stay up.
So we're gonna shake it a bunch and then centrifuge it?
Yeah.
Okay. Are we not using the vortex thing?
What's that? Oh, the vortex thing? Yeah, you can. You can use the vortex thing. I never do. That's just as easy. There are some applications with the vortex thing, mostly in biochemistry, where it is, and they have very specific. Okay, vortex this for 2 minutes or whatever. So, in a liquid extraction of organic chemicals, you're going to get your desired results in a few moments of shaking. Okay. By the way, what's molarity? I know this is totally basic, but sometimes it's good to review the basics, yeah?
Moles really good.
Yeah. It's moles of solute over liters of solution. Just see where we're at.
The whole solution?
What's that?
The whole, over.
The whole solution, yeah, exactly. So technically, the methyl violet adds to that volume, but you know, in solutions like this, it doesn't add very much. Okay. By the way, something I never teach my gen chemers this, but you guys are advanced, so you're ready to know this. Molarity is moles per liter. It is also millimoles per milliliter. Okay, and that's sometimes more convenient because a lot of the time in the lab we're working on the level of milliliters rather than liters. Okay, and we have so it equals the exact same thing. Okay, and if that seems weird, maybe it doesn't seem weird, but all we've done is we've multiplied the top and bottom by 1,000. Okay, if you do it to the same to the top and bottom, and you don't change the value, right? Okay, beautiful. All right, so mix two solutions, solvents. Okay, this is an extraction that are immiscible. Okay. And solutes move from one solution to another. All right. Part. Oh wait, nope. I'm not ready to do that yet. Okay. We want to know, by the way, how much is left in the aqueous layer. Okay. So then we're going to check what's left in the aqueous, AQ layer, bottom layer. Okay. This, by the way, we'll title that, what's left in the aqueous layer, as extract A. Titling it extract A because later on there's going to be an extract B. Okay? But again, extract A, even though we have removed some of the methyl violet, it's still too concentrated to put in these machines. So we're going to do the same trick. We're going to take a volumetric flask. We're going to put in some of extract A. We're going to put in, fill it up to the thing. Still too concentrated. Dilute to extract A diluted. Just as we did in part 2, we can figure out the concentration. Now we can measure the absorbance for that. Then we can figure out the concentration of this. But that's not what we want to know. We want to know that, but we can do this with math. Once we know the concentration of that, we can figure that out through math. Okay? All right. We will also want to know what's left, what's gone into the organic layer. That may seem like, well, you said that we can't put it in the machine. Okay. This is going to be C superscript. Yeah, superscript, gosh. Or said. He liked his symbolism. Okay. So we want to know what the concentration is in the organic layer. All right. It turns out if we know the volumes are involved, all right, we know how much methyl violet was in there. That was solution A. We figured that out in part 2. We know how much solution A was in there. If we use extract A and extract A diluted to figure out what the concentration of methyl violet in there after the extraction, okay? The only place that methyl violet, the missing methyl violet could have gone is up there. So we can actually figure out how much methyl violet is in there by essentially subtraction. Does that make sense just conceptually? Yeah. The way the math works out for that is C1 org, and this is all in your procedure as well, these equations. V org plus C1 aqueous E aqueous equals C naught, that's a naught symbol, aqueous. When do we tend to use naught in science? Does anybody have any? I know that's a vague question, but we tend to use naught symbols for the initial state. It's just not a hard rule of thumb, but often it's used to describe the initial state. Okay? Okay, so what do you think? What do you think C naught aqueous is?
Solution A?
Yeah, that's the concentration of solution A. Okay. Yeah, I told you the volumes, right? So what's B aqueous? How much solution A do we use in this extraction? I mentioned it. It's 3 mils. We're going to use 3 mils. All right. What do you think this is?
The octanol?
Yeah, that's the concentration in 2-octanol. Okay?
Of methyl violet?
Which is extract A. What's that?
Is that the concentration of
Yes,
methyl
that's,
violet?
yeah. And what's that? Do you avoid?
3.
That's 3 again, yeah. Okay. Oh, I'm so sorry. That's not extract A. Okay. This is extract A. That's how much concentration after you've done the extract. Okay? Sort of state 1. Okay. So, concentration of extract. Okay. Okay?
Is it the extract? Oh, because we can find the extract A from the extract A diluted.
Yep. And that's 3. Okay. All right, just real quick why this works, why this equation works. This is the concentration of solution A times the volume of solution A. What does that give you when you multiply a molarity times a volume? Use my new symbolism. This is yeah, exactly. I'm gonna use my thing millimoles. Okay, initial millimoles of solution A. Okay. All right. Then this is the millimoles of methyl violet left in aqueous layer. Okay. Remember moles, millimoles, all that. It's just a big number of molecules, right? So here's the initial number of molecules you have in solution A. The initial molecules that you have, or the molecules left in the aqueous layer. So this is the molecules that went into the organic layer. All right. So essentially, I would suggest you solve this equation for that. That's what you're trying to. That's what you're using this equation to determine. Solve for that before you plug junk in. Okay. Millimole that went to the organic layer. Okay. All right. One more quick little thing. Oh, that was supposed to be. This was supposed to be B. What went to organic layer? Okay. Now C is which layer is preferred? We initially started with the methyl violet in the aqueous layer, but once we do that extraction, you're essentially giving methyl violet the choice. It can be in whichever one it wants. Okay? So now that we've figured out how much is in the organic layer, okay, we can come up with a value. All right? So that is going to be our partition coefficient, KD. And that's just simply going to be the ratio of C1, or this is arbitrary, but if this is how KD is done, organic layer over aqueous layer. So after the extraction, what's the concentration in the organic? What's the concentration in the aqueous extract? Okay. What's the units of your partition coefficient? It's unitless. Very good. They both got the same. So if KD is less than 1, all right, which one does it prefer? The aqueous layer. Yeah, if it's less than 1, that means the denominator is bigger than the numerator. And then, of course, the opposite is true if it's greater than 1. If it's greater than 1, it prefers the organic layer. Okay. All right, almost done, guys. Okay. Part 4. Okay. And in part 4, what we're going to do is efficiency of multiple smaller extractions versus one larger extraction. Okay. We're going to see what's more efficient. To do extractions, to do multiple extractions, or to do one large one. All right. It turns out, if you know your partition coefficient, you know that's a value that describes which one it prefers. You can actually figure out how much is going to be left in the aqueous layer. And if you know what the volumes that you plan to do, you can come up with a theoretical value that should be left in the aqueous layer. A lot of time in these science lab classes, we okay, here's the theoretical value. Now go do the experimental value. You do it out there and stuff, and then you compare the two. This is one of those situations. Okay? So, predicted. Okay? You already did the one larger. That was part 3. Okay? Now, we're going to think about doing a multiple small ones. So C sub n left in the aqueous. This is the concentration left in the aqueous after n extractions. Okay. All right, so, like I said, if you know the KD, you can actually come up with a theoretical value for just that first extraction you did in part 2. Is that part 2? No, sorry, part 3. Well, that sucks. Okay, I don't need it. I'm okay. Damn, there it is. Okay, so, for what you did in part 3, all right, the extraction. What's n?
Number of extractions.
Right. So what is it? It was just 1, right? You did 1. Okay. And what is this? C not aqueous.
Initial
Concentration.
of the aqueous state.
What phrase are we using to describe that? That's solution A. So that's the concentration of solution A that you figured out way back in part 2. Okay. All right. What was VAQ? Specifically, no.
3? No.
3. Yeah. VAQ again. What was VOR? 3. Yeah. KD is KD, and that's the concentration that's on. All right. Now we want to compare that to, well, what if we did it 2 times? And by the way, I've had students do it 2 times and put brand new solution A's in there in between. Okay, the whole point is to extract the same sample of solution A 2 times. So don't change that. All right, got it. Okay, so you got your solution A, you got your octanol. The second time what you're going to do is rather than add 3 mils of octanol, you're going to add 1.5 mils of octanol. Okay? You're going to shake, shake, shake. Okay? And this time, before you remove the bottom layer, you put a disposable pipette down to the bottom, and you remove the bottom layer. Now you're going to remove that top octanol, and just going to put it aside. You don't need it. Okay? You didn't need the other octanol either. Okay? Then you're going to put in 1.5 mils of fresh octanol. Okay? And you're going to extract it again. Okay? And then centrifuge it again. And now you can take some of that bottom layer. Now you've extracted it 2 times. Okay? And you can see how much is left in there after 2 times. You can compare it to part 2 where you just did it 1 large time. Okay? So in that scenario, right, let's think about this. What is VAQ? What's that?
3.
It's 3. What is VOR?
3.
1.5. Yeah. What's N?
2.
2. What's this?
Initial action.
Yeah, it didn't change. It's concentration of solution N. Okay, KD is KD. And that's how many extractions you have after 2 extractions. Okay? All right. So you're going to, when you, and by the way, the calculations do at home. Don't slow yourself down by doing the, there's no advantage to doing them while you're in here. All right? So, but once at home, when you're doing the worksheet, you will come up with your theoretical, okay? And then you will, and then you're actually going to do in part 4, you're going to do 2 small injections. Questions, guys? Okay. Right on. Yeah, I totally toasted these things.
Oops, sorry.